Okay, we come to the last group that we're going to look at for today, which is halogenoalkanes. So halogenoalkanes, uh, what is the general reactivity is that I will draw you one example, which is chloroethane. Okay, chloroethane. So you can see uh, there's a partially positive carbon and a partially negative chlorine. So in this case, you can see most halogenoalkanes, they are susceptible to a nucleophilic substitution because of the electrophilic carbon of the CX bond. And usually they undergo substitution because note that carbon have four bonds. Carbon, what is going on? Okay, I'm back. So carbon have four bonds. Alright. And thus if I were to attack this using a nucleophile and not break any bonds, it will result in the carbon to have five bonds, which is a no-go. So that's why we always have to uh push out the chlorine atom as a chloride anion. Okay? So another thing is that there's this thing called halogenoarenes, which is looks like this. Okay? So there are actually four factors, and you can use any one of the four factors to explain its general lack of reactivity towards nucleophilic substitution. So the thing you have to focus on is the side-on overlap of the p orbitals on the halogen, as well as uh the pi electron cloud of the benzene ring. Okay? And this causes delocalization of the lone pair on chlorine across the benzene ring, causing a partial uh double covalent bond, and this strengthens the CX bond, okay, making it more difficult to cleave, and thus the C atom is less susceptible to the nucleophilic attack. Okay, the steric hindrance factor, you can talk about how the rear side is being blocked by the bulky benzene ring. So normally you would have something like this, right, where they'll perform a backside attack. The nucleophile will perform a backside attack. However, if you're talking about a nucleophilic uh, benzene ring, right, where there's the electron clouds above and below the benzene ring, it's very hard to attack this carbon right here to push out this. You imagine that the electron clouds are above and below, okay? They are all above and below. So if a nucleophile want to come in, it's gonna be very hard. Which brings me to the point that the nucleophile and the electron cloud of the pi electron cloud, they will repel away from each other. So it makes it even more difficult. Okay? We can also talk about the percentage S character of the hybrid orbitals involved. This factor, usually is, I would say out of H2 syllabus. I don't think I see this factor a lot. But if in the case that you need to use S character to explain, if they give you a novel context, then you can consider this factor. Okay? So sp2 hybrid carbon contains more s character because sp2 hybrid carbon there's one s orbital involved and two p orbital involved, while sp3 is one s and three p orbitals. So you can see this one is 33% s, this one is 25% s. Okay, so because of a stronger s character, you think about it, usually the energy level of s orbitals are lower than the energy level of p orbitals. So that is why we say that the bonding electrons of CX bond is more closely held to the nucleus. Okay, and sp2 CX bond are stronger and more difficult to cleave. Alright, elimination, usually we don't uh usually for elimination we don't undergo elimination of the halogenoarenes because it will disrupt the resonance stability, okay, or the aromatic stability, which requires a lot of energy. Okay, so imagine if you end up, I don't think this one should not be in the syllabus, but in case they ask about it, right? If I give you this and I have a base, then this product will be formed, which is actually very, very unstable because you can see that there's this portion right here is supposed to be linear, but because of the geometry of the benzene ring, it is forced to be bent a bit. So this one is actually very unstable, and thus your POE actually shifts more to the left. Okay, so this is why we don't really undergo elimination for halogenoarenes. Okay, this part you can just read it yourself. Okay, for the first one we see the bromine atom being substituted by the OH. Okay, and the reagents and conditions are as such. Sodium hydroxide or potassium hydroxide, a strong base. Okay, a strong base so that you can push out your Br. Okay, and we usually heat under reflux because the CBr or CX bond, CBr, CCl bonds, they are generally have because it's a sigma bond, right? It's very strong. So the conditions used, I would want it to be a lot harsher. Okay, the mechanism I'll show you later when I go through the SN1 and SN2 mechanism in small detail. But the remarks portion, we can see that actually if you want to form an alcohol from halogenoalkanes, you can also use water. But the reaction will be a lot slower because it's a weaker nucleophile since it's not negatively charged. And water, just a fun fact, is usually a good solvent to use for this reaction for nucleophilic substitution because they are small and less bulky. So if you think about it, your OH minus can actually form ion dipole interactions with water. Okay, so just imagine many water molecules surrounded by OH minus. Okay, and since H2O is a very small and less bulky species, it is easier for a nucleophilic backside attack of the OH minus because less because this whole entire thing right here is less sterically hindered. And I will explain this when we go to elimination where we use a alcohol medium, and we will see that actually an alcohol, because it's more bulkier, it would be more sterically it will sterically hinder the OH minus anion and make it harder for the nucleophilic backside attack to occur. And thus we always use the OH minus in the alcohol medium as a base. Heating under reflux is usually the purpose is we want to continuously heat the reagents with the reactants and prevent these organic compounds that are very volatile from boiling off. You know, organic compounds, they generally have a low melting point uh, and low boiling point because of weak intermolecular forces of attraction between the organic molecules. So if I am able to prevent volatile components from boiling off, it will always condense back into the reaction mixture and cause the reaction to go to completion. And we always heat at a constant temperature, okay? And any vapor will be condensed back. So next part, alcoholic or ethanolic uh NaCN, where the Cl is being replaced by the Cn. Okay, simple as that. Heat under reflux is the same thing. The mechanism I'll go through later, but the remarks portion, because Cn, we are adding, we can see this reaction as a step up reaction. So whenever if you want to add more carbon atoms, right, always look at uh Cn, so your nitriles. Alright. The next part is excess. This part is the to add NH2 and replace the Br with NH2. So in this case, heat in a sealed tube and use excess ethanolic NH3. Okay? So this is because you want a high yield of primary amine and prevent further nucleophilic substitution. I'll explain why in the next reaction box. But basically, in what you have to focus on is the Br being substituted by NH2, and the one more NH3 is being used to protonate. It's not protonate. The NH3 is being used as a base to gain a proton from this area. Okay? The protons transfer causes NH4 Br to form instead of HBr to form. Right? We can see NH3 to be a stronger base than the Br minus, even though generally NH3 is a weaker base. And this is because I know Br minus have a negative charge, but if you think about it, Br minus is the conjugate base of the strong acid HBr. Is the conjugate base of strong acid HBr. So Br minus would not likely gain a proton to form back HBr. Okay? The chances of that happening is very negligible. So that is why we always refer to NH3 as a stronger base. And that's why we always use NH3 to gain a proton. Okay? Substitution will stop when the quaternary aluminum salt is formed because there is no more lone pairs available on the nitrogen atom to attack the electron deficient carbon. Okay? And the reason why the possibility of further nucleophilic substitution happening is because the product form has a lone pair of electrons, and it also acts as a stronger nucleophile because of the electron donating alkyl group that increases the electron density on the nitrogen, making the lone pair of electrons actually more available. Alright, And the heat in the CO2, do note that this only applies if you are using nitrogen compounds or amines that are less than 4 carbon atoms. Okay, only applies for less than 4 carbon atoms. And this is to prevent the gas from escaping, allowing the reaction to go to completion. So if example, I give this as a reagent instead of NH3 gas, so your condition would instead be heat under reflux instead of saying heat in a sealed tube, because there is no gas that would likely to be escaped. Okay, because this one is no, I wouldn't say this confirm cannot be a gas. It's more than 4 carbons. Alright, so this is why you should not use limiting, is because you can see how this product, okay, this is not the final product. This product right here, you see that electron donating ethyl group makes this lone pair more available, and thus this will continue to perform a nucleophilic attack on the original reactant to form a secondary amine, then tertiary amine, and a quaternary ammonium salt. And in the quaternary ammonium salt, no more lone pairs, so that's when nucleophilic substitution will stop. Okay, for this reaction, it's an extension reaction. So in this case, I would say the what we are presented right here is CH3OH and CH3O minus, so alkoxide and alcohol. So when you see sodium metal reacting with alcohol, we will first say that CH3O minus forms. Okay? Alternatively, you can use CH3O minus also. Alright? Then one condition they say heat, one condition they say at room temperature. Alright. And the reason why you want to heat for the first condition is really just to make sure I am able to deprotonate the alcohol group. Okay? So this is the mechanism. We show the nucleophile electron rich attack the electron poor or electron deficient carbon of the CBr bond, and this transition state forms. Alright, and then the Br minus is left, and this shows the ether group being formed. Okay, you can also use the alcohol as a nucleophile. However, you take note this is somewhat similar to when you use NH2 to replace Br, whereby your hydrogen must be uh, abstracted by the another alcohol molecule. Okay, so that you form the ether product. Right. And same reasoning, I would say that the CH3OH is generally more, is the lone pair on oxygen probably more readily, because as I said, the Br is a conjugate base. So this conjugate base is negligible to gain a proton, since it's a conjugate base of the strong acid. Next up, this is SN1 reaction, so let's go through how this mechanism works. So SN1, what this means is that S is substitution, N refers to nucleophilic, and 1 means that there is one molecule in the rate determining step. Just take note, 1 does not mean one step, alright? 1 means one molecule in the rate determining step. Okay? So in a sense, this is actually a unimolecular reaction whereby the only one molecule is in the rate determining step. It's not the nucleophile. So you can see the heterolytic fission of the CBr bond is slow because you're breaking a bond which requires high activation energy, forms the stable carbocation and the Br minus as a stable leaving group, and then the nucleophile will attack in the second step, where it's a fast step because uh, the positively charged carbocation is strongly attracted to the negatively charged hydroxide ion. Stereochemistry, you know that this is the same for the alkene chapter, so I will not go through too much. Kinetics, it only depends on the concentration of the Rx. Factors affecting rate of SN1 reaction. This one is about the same as alkenes, whereby the more electron donating groups, the positive charge on the carbocation is dispersed to a much greater extent and thus it stabilizes the carbocation. And then we can look at these two examples. I think I go through this in one of the Erin's notes videos. So just know that whenever there's a overlap between a continuous overlap between p orbitals, you have delocalization. And delocalization of electrons means you can disperse your positive charge to stabilize the carbocation. Same for this benzyl halides. Disperse, positive charge, stabilize, overlap, and delocalize. So just take note of all these keywords, alright? And I would say the benzyl carbocation is more stable than the allylic because there's the positive charge is being dispersed to across more carbon atoms. Okay? Another factor is the strength of the CX bond. This one uh is self-explanatory. You have to see that focus on the size of the halogen and the bond length when the valence orbital being used for bonding is more diffuse, right? The effectiveness of the orbital overlap is less effective. Okay, less effective. So this means the bond strength will be lesser, bond energy lesser, and rate will be lesser. Okay. CF bond normally don't go through because it's very strong. So no nucleophilic substitution. Alright, for SN2, right here, focus on the 2 represents two molecules in rate determining step. Okay? So the electron rich species attack the electron deficient species to push out the Br minus. And take note, usually you have to draw a transition state. So transition state, what you need to focus on is the dipoles, this transition state symbol, as well as the bonds forming and breaking using dotted lines. Okay? Normally your oxygen and Br, they adopt a partial negative charge because you have the nucleophile forming a bond. The nucleophile is negatively charged, right? So it will form a bond with the electrophilic carbon. So in that sense, the negative charge on the nucleophile would decrease. That's why I give it a partial negative. And then the bromine is gonna leave as a negatively charged anion product. So in a sense, the negatively charged is starting to form. So that's why I give it a partial negative charge. Okay. For stereochemistry, we focus on the keywords backside attack of the nucleophile on the rear side of the CX bond, causing an inversion of stereochemistry with respect to the chiral carbon that is where the substitution occurs. Okay? Depends on the concentration of both Rx and nucleophile. This one should not be SN1. This one should be SN2. I bet. Okay. The steric factor, electronic factor. So steric factor first. If you have more electron donating groups bonded to the electrophilic carbon, it means that there's a lot of steric hindrance. So it's more difficult for the nucleophile to approach it. Another bad reason is that uh because of more electron donating alkyl groups increase the electron density on the electrophilic carbon, thus less electron deficient and less attracted to the attacking nucleophile. The strength of CX bond I gone through already, so it should be the same. Elimination reaction. The reason why we use alcoholic and ethanolic is because ethanolic and alcohols, when they form hydrogen bonds and ion dipole interaction with the OH minus right here, you have a very sterically hindered uh species in a sense. So your OH minus is much more sterically hindered, and thus they can only act as a base in alcohol medium. Alright, so heat under reflux, same reason because of the sigma, the CCl sigma bond that you have to break, and it's sort of a high activation energy you have to overcome. The chemical equation, this is the chemical equation. So the OH minus, you can see it. Let me go a bit closer. Alright, so the hydrogen, okay, this is too large. The hydrogen, this one will abstract out the hydrogen, form a double bond, and then the Cl will leave as a Cl minus. So this will help to form water. This will form water, whereas Cl minus goes with Cl minus goes with the sodium to form sodium chloride. Okay, so this is how you construct, and then you can see that uh this Cl right here, right? I change ink. This Cl right here is you can see that there are hydrogens here, here, and here. So I have three possible hydrogen position whereby I can abstract the proton from to form the double bond. Okay, so in this case, that's why it results in many different organic product form. So if I abstract uh this proton right here, I will form the major product. If I abstract this proton right here, I will form this product right here, and take note, I can form the trans and the cis. Okay, and if I abstract this proton right here, I will form this least stable product because there's only two alkyl groups that is bonded to it. So the Sayzev rule, right? The more substitution the double bond is, the more stable it is, and the faster the reaction rate and yield of the major product. And this is because the alkyl groups are electron donating, so it actually uh increases the electron density and accumulate the electron density of the alkene bond, the alkene group. Okay, Note that the trans isomer is more stable because there's less steric hindrance. So you can see the two groups are the two largest groups on both sides. They are furthest apart. Alright. Okay, distinguishing tests with different halides. So first method is the production of silver halide precipitate and its solubility in water. So what I will do is that I will add NaOH and heat it. Do not say heat under reflux because this is a distinguishing test and it's not an organic synthesis. Okay, so reject heat under reflux. Okay, so addition of NaOH is ready to cause a nucleophilic substitution to release the halogen as a halide. Once I release the halide and ion, I will use excess HNO3 at room temperature so that I will prevent the formation of a silver oxide or silver uh, hydroxide because your sodium hydroxide can react with this Ag plus here to form silver oxides or silver hydroxide. And that's not what we want. What we want is the Ag plus from AgNO3 to react with the halide and ion that was produced from the nucleophilic substitution of halogenoalkanes. Alright, so once I form my precipitate, some people will say, hey, bruh, it's not that clear, right? Like, got one yellow, got one cream, and got one white, then you colorblind, you don't know what are. You can use NH3 so that I'll be able to see clearly which one is to identify the halide much more easily. So if I use RCl, the AgCl precipitate, the silver chloride precipitate will be dissolved in aqueous ammonia to form a colorless solution. Okay, it will form, just to recall, right? It will help to form this transition com metal complex. All right. So chlorobenzene no precipitate because of the reason that the CCl bond is very strong. Okay, so this should be it. And yeah, this should be it for the first method. The second method, we using ethanolic silver nitrate or ethanolic silver ethanoate and heat it up. The ethanolic solvent is to increase the solubility of organic RX. So you can see this is RX, right? This RX can form ID with the alkyl portion of the alcohol, and this X or the halogen, right, can form PDPD with either water, either water or the OH part of ethanol. Okay, so because of this formation of the forces of attraction, thus it compensates the is enough to break the strong hydrogen bonds between the ethanol molecules and the water molecules. Okay, water acts as a weak nucleophile so that the relative rates of substitution can be easily observed. Okay, so that is why we have an ethanolic solvent. So just take note, uh, the rate of formation of Rx can be explained using the strength of the CX bond. Alright, for primary, tertiary, and secondary halogenoalkanes, we use the same method as before, and we can see that for the primary Rx, is the slowest reaction because in ethanol, you'll see that ethanol slows down the SN2 reaction because it forms hydrogen bonds with the reactant that is water and hinders the backside attack of the nucleophile on the electrophilic carbon. So what I'm talking about is basically what I have shown in the above diagram. Okay, this diagram over here. Okay, this diagram over here is what I'm talking about. Just that instead of the OH minus, it will be a water molecule surrounded by the ethanol molecule. And this hinders the backside attack on the electrophilic carbon. And since SN2 depends on the concentration of the nucleophile, that is why it is a slower reaction. Okay. For tertiary alkylates, we always say that it goes through SN1, right? And it is independent of the concentration of the nucleophile. That's why presence of ethanol, they don't care. They will just proceed ahead. Okay. For this stuff, the main focus right here is that uh the CFCs are inert, okay, because of the strong CF bonds. Alright. And they will deplete the ozone layer. For the measures to reduce ozone depletion, usually we will try to use uh substitutes such as hydrocarbon, hydrofluorocarbons, and fluorocarbons because CF bonds are quite strong. So they won't really uh undergo any free radical substitution and attack and deplete the ozone layer. Okay? So this is the notes I'll go through. Oh wait, there's also nitriles. Alright, I'll go through nitriles quickly. So nitriles, note that it can undergo a nucleophilic attack by water because you have a partial positive on the carbon right here and a partial negative on the nitrogen right here. Okay? It's also very susceptible to reduction because you can see the oxidation state of carbon is actually quite high. It's around +3. So I would want to reduce it to a lower oxidation state. Okay? This, you can read it yourself. Uh, this is acidic hydrolysis. So basically, we are using the dilute acid to hydrolyze this CN group, this nitrile group right here, to form COOH. Alright. And because benzoic acid is formed, a white precipitate is therefore formed. Alright. So how this with the heat under reflux also, how this occurs, I can show you right here. What I suspect, if you're gonna go through, let's take for instance this. No, is I would want the water to attack because water acts as a nucleophile. Okay. I can also choose to protonate the N using H plus to make this as a to make this carbon a stronger electrophile or to make it less electron to make it more electron deficient. Okay. So to So this one will be a positive charge. Okay. My water molecule attacks. And thus this causes this to form. Okay. Let the arrows do the work. So alright, so what I'm gonna do next is this. Nitrogen has a lone pair. Abstract the hydrogen right here. This, let's see, what else can I do here? The lone pair can go down from this. To form this. Okay. This one will go over here. NH3 plus. And I will have another water molecule to go attack the carbon and cause the NH3 plus to leave. Okay. So I'm just saying, look at how my arrows go, and this is how I usually try to derive the product. Okay. So this is plus, right? So what I'll do is this NH3 have a lone pair. We'll extract this to form the desired product. Okay, that's why NH4 plus is actually formed. Okay, I'm saying this one is not good. I don't know whether they would. I don't think they would test mechanisms. This mechanism is not going to be tested in the A levels, but I'm just showing you this mechanism I say ahead. It's not saying that it's confirmed correct also, but I'm just saying that uh I can propose a reasonable arrow pushing so that I can at least know roughly what my final product is, which is the COOH and the MH4 plus. Okay? Let's go down. Alkaline hydrolysis. Okay, so this part, right? What I initially tell you guys to do is that draw all the organic product. So in this case, we are using KMnO4 and sodium hydroxide. So KMnO4 is a strong oxidizing agent. So you can see the alkenes will confirm be oxidized. This one. NaOH is used. So this one will be converted to a COO minus. And don't forget the Cl will also be converted to OH. Okay. And because I'm using a strong oxidizing agent, after converting this to an OH, I'll need to oxidize it. This one is a secondary uh alcohol, so I'll need to oxidize it. Tertiary alcohols don't need to oxidize it because we do not have a hydrogen that can be removed. Okay. And as a result, this is the organic products that are being formed. Alright. Note that NH3 is also produced, and this comes from the N atom of the nitrile group. Okay, so the pungent gas turns damn litmus paper blue. For reduction, this is the reagents that we use, and we represent the bracket H to show there is a reduction, to show that there's a gain in hydrogen. As per normal, I would say that uh this triple bond, I would want to convert it to a saturated molecule. So I remove this. So what I do is I remove one of the bonds. It works like the reduction of alkenes. So remove one bond, form two hydrogen, remove the second bond, remove the second bond, and add two hydrogens. Okay? The regions and conditions uh is the same as that for alkenes. Okay? So I'll not go through too much. AlH4 minus, this is a common reducing agent. This is a very strong one indeed. A strong reducing agent. So that's why it's able to reduce uh nitrile, which has highest oxidation state of carbon. Okay, this one normally I wouldn't say that. I don't see this being used as a reagent, so this one is a FYI. The common ones to remember are these three. Alright, okay, that's it for this crash course. If you make it out alive, congratulations. I will go through the notes. I will go through the questions, some of the questions that I believe it's slightly more difficult. Okay, so I'll be right back. Bye.